Okay, so we are on the last part of 2A.5, which is the natural base E. And basically, E is a number like pi. Okay. E is approximately 2.718. And so you treat it as a number, okay, not as a variable. And so the natural number E is often used as a base in exponential functions that model contextual scenarios, basically things that are continuous, like are going on, or it's just a general thing that's happening around you in nature or whatever. So when you are solving, there is a way to estimate or kind of convert between the two of exponent of E base E and non-base E problems. Okay, so up here we have, it says the number of bacteria in a particular culture can be, where's my pen? Culture can be modeled by the exponential B of t equals 17 times e to the 0.31 t, where t is measured in hours. If we want to let a of t be our exponential parent, a times b to the t, be an equivalent expression for b of t, find the value of b. Okay. So in order to find the value of b, the first thing we're going to do is we need to find a of 0. All right. So we're going to have to find a of 0 because, of course, we need to know that in order to find our a, right? Um, and a of 0 is going to be equivalent to b of 0. And what is b of 0? It would be 17. So we know that a of 0 is going to be 17, and that's because b of 0 is 17. Good so far? Okay. After we find that, we then are going to, what do we, this is supposed to be an A. Does it say A on your paper? Or say B? It should just be A. We found our A. Then we're going to find our average rate of change. We need to find the average rate of change because that's going to help us lead to finding our B for our B of T estimation. So finding the average rate of change. Do you guys remember how to find average rate of change? Good old A rock. Okay. So we're looking for the A rock of from B to 7, B of 1, which is going to be 7 minus 1. That's a little funky B. So remember I told you were going to need your calculator out? This is why. So we have to use the B to find B of 7 and B of 1, and then we're finding their difference. Obviously, we can do 7 minus 1 in our head, which is simply 6, right? Easy peasy. All right, so we're going to go on. Yes, thank you. I don't know why those words weren't coming out of my mouth. So we have 17, and to get E, it's second ln, 31 hundredths, and x. So that is my y of 1. So I'm going to go to my calculator homepage, and I need to find b of 7 minus b of 1. So I'm looking for, I'm going to hit alpha trace y1 of 7 minus alpha trace y1 of 1. Because my y1 is my b, and I'm going to let it do the math. So I get 125.713. And I'm going to divide that by 6. And so my A rock is approximately 20 and 952 thousandths. So that means that it's changing. The average rate change from B of 7 to B of 1 is roughly 20 and 952. So now I have a rate that's taking place. Does that make sense? So I know how it's changing. I know how it's where it starts. So do I have enough information to try to figure out what a possible model could be? In theory, we do. This is assuming that your teacher is remembering this correctly, by the way. We hope she is. I think that's all I'm supposed to tell you to do. Yeah. Oh, now we just find the number of bacteria predicted at the model after 15 hours. Yeah, that's all we had to do. So I just wanted you to be able to understand that the bases are going to be the same, or that should have been the A, not the B. The A's are going to be the same when you're finding the model. And then average rate of change can still be calculated. And we're supposed to go over just using the model to find our solutions. So we're at 15 hours. So it says find the number of bacteria predicted by the model after 15 hours. Well, that's just your T, right? So do you see how in this in the calculator homepage, I can utilize alpha trace one and use find 15. And that would be my prediction. I'm supposed to also model this in Desmos. So therefore, B of 15 equals 1,707.94. Okay. I know it's not on here, but I kind of want to talk about this. What if they gave me the bacteria, right? If I was given bacteria, what would I do to find out the time? Exactly. So even though it's not on here, I just want to make sure that we're comfortable being able to find that. If I told you that I have B of T equals 1,000, could you find the T that makes that true? Do we all feel confident enough doing that? Okay. If it's a calculator question, then it's simply a what that you're looking for. It would be an intersection. If it's a calculator question, it's an intersection. If it's solving by hand, it's inverse operations. What do you need to do to get your variable by its self? So if I had B of T equals 1,000 and I'm asking you to find T, we would be setting this equal to 17 e to the 3100ths T, right? If I'm solving it by hand, cool. I would divide by 17. I would take the natural log, bring out those algebra 2 skills, right? But more than likely, this would be on a calculator part. If I have the calculator, they want you to use the calculator. That's where you would go in and put your Y value in, and you're looking for that point of intersection. So when I'm doing that, if you want to see if the calculator can help you zoom in a little faster, that's the zoom fit. More than likely, you guys would be using what? Desmos, because you guys are haters about Sylvie and her grandchildren. And so let me model that on Desmos just to recap how to do it. Y'all are Sylvie haters. But you see how much easier it is to have her on the page at the same time while I'm teaching you? Desmos doesn't do that. It doesn't have a little teachable thing. All right. So here, when you are wanting to utilize the features that we were using with Sylvie, you have to make sure that you're inputting it in as f of x. If you're not inputting it as f of x, you won't be able to use function notation to evaluate. Does that make sense? So I'm going to put in f of x equals 17 e shift 6 to the 3100 t x the t. Okay, there she is. Boom. Okay, so using here again, if I wanted to find that average rate of change, I do like the fact that it is a little quicker to make a. Did they take away the little fraction bar button? on the calculator page? Oh, well, it used to have like the thing over it. Um, but either way, anyways, we go on. Here, so now if I was looking for the average rate of change, I would write f of 7 minus f of 1 over 7 minus 1. And that's because I wrote it in function notation. Because I wrote it in function notation, I can use function input, the input feature, for it to calculate. Does that make sense? Okay. So there's that. On the next part, when it asks you for f of t, that would just be simply of doing f of 15. And what do we get? Said value. Correct? All right. Next, I said, what if I told you by bacteria, right? I'm asking you, and I said there's 1,000 bacteria. When I'm giving you the bacteria, I'm giving you your f of x, right? I'm asking you when f of x equals 1,000. And when I ask you about when f of x equals 1,000, I need to call this something else so that it doesn't get confused. Remember, you can rename your functions. Functions can be called multiple things. Okay. So do you see when I tried to call this f of x, what did it do? Oh no, it's too many of us. Okay. So I simply changed it to g of x. All right. I need to find 1,000. Just gonna scroll out. I can scroll out. You cannot, and all you're doing is looking for where that intersects. And that would be your solution. It doesn't have to be pretty when you look at it. As long as you can find where they intersect, guess what? All right. So remember I told you that 2A.5 is pretty calculator heavy? This is why. All right. Questions so far about example 4. Do you feel confident in doing all the things that we just did using whether TI-84, because it wasn't bad in Sylvie, or your Desmos? No questions? We're chilling? Okay. All right, let's go to example 5. So for example 5, we have somebody else read.
Population of deer in this area can be modeled by the exponential function b of t equals a times b to the t, where t represents the number of deer since deer were first introduced to the wooded area. The population of deer increases by 13% each year.
Perfect. All right, so here we have it says first find your a and your b and use these values to write an expression of d of t. So do you remember how I said that this is where you have to set up those two equations? When we talk about setting up those two equations, and when we're setting up the two equations, it's based off of us using the given information. So our given information is that we are using an exponential model, right? So we're going to set up the exponential model using what we know. It says years since deer were first introduced to wooded acre, the population of deer increased by 13% each year. So we know that it's increasing by 13% each year, and it started where? At 50. Okay. So our first equation that we would have would be our d of 0. That's where it starts, right? We start at 0, which would be a times b to the 0 equals what? At 0, we had what? 50. Agree? No one's like, Miss Jones, you made that up. Okay, good. All right, next, after 1 year, they notice that it increases by what? 13%. So this is where it gets interesting. So we have our d of 1 is going to equal, well, we know our initial. What was our initial? 50. And our b, we can figure it out because we know that it's a steady increase. It's an increase. And when we talked about this, goes back to being an Algebra 2 problem technically. If I am at 100%, that's our starting point, right? And we're either an exponential growth or an exponential decay. In this case, we are a growth. So when we are figuring out what our second model would be, we're paying attention to the fact that it's 1 plus or minus something, right? 1 plus or minus your rate. In this case, it's going to be plus our rate. And it's plus our rate because it's growing, it's growth. So this is going to be 1 plus 0.13. Make sense? And the power on this is 1. So by the time we get to year 1, we know pretty much everything we need to about the problem. Okay? So because of this 1 plus 1, 3, what is our B? 1.13. So can I write a model that I can use for the remainder of the problem? I surely can. What would my model be? Perfect. D of t equals 50 times 1.13 to the t. And that's my model that I would use for the rest of the problem. Okay. So according to this model that we found, what would the population be after 6 years? Well, so we're looking for D of 6, which would equal 50 times 1.13 to the 6. And we would just plug that in the calculator and we get our approximate amount of deer. And what do we get? I'm going to let you all, because unless y'all want me to do it with Sylvie, I'll model it with Sylvie for you. Sounds right. Let's see what Sylvie gets. 50 times 1 and 1300ths to the 6. Oh, Sylvie and decimals got the same thing, guys. Surprise. We get 104, and that's what I was about to ask you. So we're talking about animals. Can you have 104 and 98 thousandths of a deer? No, you cannot. So approximately it would be what? 104 deers. Okay. So my understanding for points, write your approximate, then write the real world response. Does that make sense? It's how I'm interpreting what I see in life. So we have our approximate, and then we have our real world interpretation of the problem. All right. On C, what do y'all need to do? So we want to go from years to months. That's it. You did it. How many months are in a year? 12. So what do I need to do to the years? Divide them. So it'll be D of T equals 50 times 1.13. And instead of years, we want months. You wanted it to be harder, didn't you? It wasn't. Sorry to disappoint you. All right, how do we feel about 2A.5? Okay, remember it is our calculator heavy of this unit. So if it can be done in the calculator, you do it in the calculator. All right.